Hello class, welcome to the second lecture of Input-Output Organization. If you remember, in the first class, we talked about the various input and output devices and how exactly the input and output is carried out between the CPU and the peripheral devices. We saw that in order to perform the input and output operation, we need an interface which will work to bridge the gap or the marked differences between the CPU and the peripheral devices. We saw how the interface works. Just to recap, we saw that the interface was essentially made up of four components. One was the address decoder, one was the control component, status component, and the buffer component. We saw, we also discussed how the entire process of the input and output organization takes place. Now in this lecture, we will talk about some categorizations of input and output. The input and output that is performed between the CPU and the peripheral devices can be performed in a number of ways. Now these categorizations that we talk about, they are independent in nature, right? Now the input-output processes that are carried out between the CPU and the various peripheral devices may be categorized in four essential ways. First, we have the isolated I/O versus the memory mapped I/O. This categorization depends upon how the CPU is communicating with the I/O devices vis-a-vis the communication between the CPU and the memory devices. Second, we have the synchronous versus asynchronous input and output. This categorization essentially talks about whether the clock that is governing the CPU and the clock that is governing the peripheral devices, they are working on the same frequency or not. Serial versus parallel I/O. This essentially talks about the various bits of the message, the various bits of the communication between the CPU and the peripheral devices. Are they being transmitted one by one or are they being transmitted parallelly? And finally, we have three main modes of input and output vis-a-vis. One is the program controlled input and output. Second is the interrupt driven input and output. And third is the direct memory access, also called the DMA. We will talk about all these modes later. Now, as I said, that these categorizations of it are independent of each other. What I mean by that is you can have an isolated synchronous serial program controlled IO, or you may have an isolated asynchronous parallel DMA IO, or you may have a memory mapped synchronous parallel interrupt driven IO. Essentially, what I want to say is any type of mix and match is possible among these four types of categorizations. We will begin with talking about isolated versus memory mapped IO. A little bit background first. The differentiation between the isolated and the memory mapped IO springs from the input output versus memory bus. We know we have already talked about a bus is nothing but a collection of wires. The task of a bus is to primarily carry some signals. Now, there can be essentially two types of buses that a computer will use. You may have an input-output bus for communication between the CPU and the various input-output devices, and you may have a memory bus, which the CPU uses to communicate with the memory. Obviously, the input-output bus does not communicate directly with the input-output device, it does so through the interfaces. Now, there are three ways in which a computer can use these type of buses. Number one, a computer. Now, when we talk about the physical organization of the input output versus memory bus, now there are many possible options. The first option is that the computer can use a single common bus for both memory and input output interface units. Now this particular option can have two sub options. The computer may use one common bus but separate lines for each function. What I want to say over here is that the data lines or and address lines can be same for both memory as well as input output, but the control lines might be different. Or the computer may be using one common bus, that means a common address lines, common data lines, and common control lines for both the functions. On the other hand, some of the computers may decide to use two separate buses, one to communicate with memory and other to communicate with the IO interface. Now this is this difference in the two types of physical organizations that forms the basis for isolated versus memory mapped IO. But when the CPU is communicating with the input output bus, please remember what is the basic format of that. The communication between CPU and all interface units is via a common IO bus. Then the interface unit connected to a peripheral device, it has a number of data registers or which we mentioned as buffers. We have a control register and a status register. Now the CPU establishes the communication by sending a command to the peripheral and by sending the data that is to be transferred to the device or reading the data that the device is providing by the CPU. Okay, let's talk about the first categorization, that is isolated versus memory mapped IO. This diagram shows the isolated input and output scenario. You can see over here we have the CPU, we have the memory, that is the main memory, RAM or ROM. We have the input output bus having the data lines, address lines and control lines. And we have the various input and output devices which are connected to this input and output bus through their interfaces. As you can see in this diagram, there is a separate set of lines which is connecting the CPU to the memory and a separate set of line that is connecting the CPU to the input and output devices. So in case of isolated IO, the lines that are connecting the CPU to the memory and the lines that are connecting the CPU to the input output are separate. So separate input output read write control lines in addition to memory read write control lines. Now one more differentiation is that the address space that is used for memory and the address space that is used for interface or the input output devices, they are separate from each other. What this means is, what address space actually means is, this is the set of values which can be used to provide the addresses. What it essentially means is that you can have an address number 1 that can be assigned to, let us say, the device number 1, and you can have the same address number 1 that can be assigned to the memory location number 1. So in a sense, the same address values can be assigned to both memory as well as the interfaces devices. So that is why we say that the address spaces are separate for memory and they are separate for interface devices. But this separate input and output address space as compared to the memory address space necessitates the use of distinct input and output instructions. Now, if we have similar instructions for communicating with the memory and the input output devices, as the addresses space are separate, as I just said that you may have a memory location number 1 and a device number 1. If I use a common instruction to perform the communication between the CPU and the peripherals and the CPU and the memory devices, it may get confusing. So we have distinct input and output instructions. We may use input and output instructions like in and out for performing the IO transfer, whereas an instruction like move may be sufficient for the memory transfers. Now, in contrast, when I talk about the memory mapped IO, you can see over here we have a single common bus which is connecting the CPU to the memory and which is connecting the CPU to the various input output devices. Although I have not shown it over here, but these devices are connecting to the bus through their interfaces. So you can see both the memory and the IO devices are connected to the CPU through the same bus. We have the same single set of read write control lines. One more point here, the address space is common. It means that now I have the same set of values. I have just have one set of values, and out of that one set of values, I have to give addresses to both the input output devices as well as to the memory devices. That means now I cannot give the address number 1 to both memory or IO devices. What it essentially means is that, let us say I have 1,000 values available to me in address space, so I can use, let us say, the values from 1 to 10 for devices and then from 11 to 1000 for memory spaces. Now as the address space is the same, that means there is no overlapping of the addresses. The address that is given to the device and the address that is given to the memory location, they cannot be overlapped. So that means I can use the same set of instructions. There is no confusion. I can simply say read 5 and it will know that I am talking about a device. As I said that I'll be using the addresses from 1 to 10 for devices and from 11 to 1000 for memory. If I specify an instruction like read 5, the CPU knows that I'm talking about the devices. If I say write 25, it automatically knows that I'm talking about the memory. So this is the differentiation between the isolated versus memory mapped IO. Now the second categorization that we saw over there was synchronous versus asynchronous IO. Now this synchronous versus asynchronous IO essentially stems from the clock that is being used to control the CPU and the clock that is being used to control the input output devices. Now the CPU, as we have discussed in the first unit, it uses a clock for performing all its operations. Now the clock frequency, obviously, when the input output device, when the peripheral is trying to send some data to the CPU, it will also use a particular clock. Why? Because the CPU performs all the operations, any type of input output will be executed through their registers only. And the registers cannot work without a clock. So if the clock that is being used by the CPU and the IO devices and the peripherals is running on the same frequency, we can say that the clocks are same. We say that it is a synchronous IO transfer. If the clocks are different, that means if the clocks have a different frequency, then we say that we have an asynchronous IO. Now before we go any further, let's clear one thing. Now from this point onwards, we will talk about the data transfer in terms of a sender and a receiver. We'll not talk about in terms of CPU and input output devices. Now when we talk about data transfer between a sender and a receiver, now we can have two scenarios. We can have CPU as the sender and the peripheral and the output device as the receiver, or we may have the input device as the sender and CPU as the receiver. Now, if I'm talking about asynchronous data transfer between a sender and a receiver, one main concern is how to tell the destination that the sender has sent some data, or how to tell the sender that the receiver is now ready to receive the data. If it was a synchronous input output, the situation could have been very clear that I will send the data in, let us say, the 10th clock pulse, you receive the data in the 11th clock pulse. Or the receiver could have told the sender, I will be ready to accept the data in the 10th clock pulse, you send the data in the 11th clock pulse. But as it is an asynchronous mode of communication, that means the clocks have different frequencies. Now, in order to perform this, in order to achieve this, there are two essentially, we use two type of methods. One is called the Strobe method, one is called the handshaking method. Essentially, the purpose over here is when the sender is giving some data to the receiver, how does the receiver know that the data that has been placed on the data bus is a fresh piece of data or it is a old data? As I have been hammering up time and again, the bus can never be empty. If the CPU or if the sender has not put in fresh data on the bus, that does not mean that the bus is empty. The bus will contain the data that was existing previously. So the main issue over here is how does the receiver know that the sender has put in fresh piece of data, right? So for this purpose, we use two types of methods. One is called the Strobe method and one is called the handshaking method. Let's talk about them one by one. Let's start with the Strobe method. Now, Strobe essentially is just a way, while communicating between the source and the destination, it is just a way to tell the other unit that yes, the data that is there on the data bus is now a fresh piece of data. Now, the communication between the source and destination can be initiated by either by the source or the destination. If we try to take example, let us say if the CPU is acting as the source device and the output device is acting as the destination device, we may have a scenario where the CPU is establishing or CPU is initiating the communication between itself and the output device. Or it may be from the destination device also, when the output device intimates the CPU that yes, I am ready to accept the data, you can send me the data. Now let's see how Strobe works. Now, as you can see over here, I have a source unit and a destination unit. Here I have a data bus. Data bus is essentially, data bus will always go from source unit to the destination unit, irrespective of whether the transfer is initiated by source or destination. It will always go from source unit to destination unit. Now we have a strobe input from going from source unit to the destination unit. Now how the things happen is the source unit puts some data on the data bus. Now this square wave or this diagram over shows this valid data. This is the portion of the time where the data that is present on the data bus is a valid piece of data. What happens is the source unit puts the data on the data bus and initiates or enables the strobe to indicate to the destination unit that now the data that is placed on the data bus is a fresh piece of data. You can visualize it like this. The source unit puts some data on the data bus and then switches on a light. This light, the turning on of the bulb will indicate to the destination unit, yes, that the source unit has put some new piece of data on the data bus. Now I can read a fresh piece of data. After a sufficient amount of time, when the data transfer has been completed, when the source unit knows that the destination unit would have read the data, it turns the strobe off to invalidate the data. It does not mean that the data has been removed from the data bus. It simply means that now the data that is present on the data bus is no longer a valid or a fresh piece of data. Now, if the communication is established from the destination side, if you see over here, the data bus is still pointing from the source unit to the destination unit, but now the strobe is pointing from the destination unit to the source unit. Now, whenever the destination unit is ready to accept data from the source unit, it will initiate a strobe. If you see here carefully, the strobe is getting enabled a little bit earlier than the data becoming valid. It indicates that first that strobe becomes high, and once the source unit notices that the strobe has become high, which indicates that the destination unit is now ready to accept the data, it puts the valid piece of data on the data bus. After a sufficient amount of time, when the destination unit has read the data, what it does it disables the strobe and the data becomes invalid after again a specific period of time. Once again, I repeat, data becomes invalid does not mean that the data is removed from the bus. It simply means that the data that is there is no longer valid, no longer fresh. If you see the strobe operation once again, one of the basic problems with strobe, either source initiated or destination initiated, is that there is no feedback involved. Let's take the case of source initiated strobe. The source unit puts some data on the data bus and initiates the strobe. How does the source unit know that the destination unit has actually read the data? It is just an assumption that yes, I have placed some data on the data bus, I have sent the strobe signal, I am assuming that the destination has read the data. Similarly, if I'm talking about the destination initiated strobe, how does the destination unit know that the source unit has actually put in fresh piece of data? The destination unit has indicated its readiness to accept the data with the help of the strobe to the source unit, and then assuming that the data now in the data bus is a fresh piece of data that has been placed there by the source unit, it will read the data. But what is the guarantee? You don't know whether the source unit has actually seen the strobe signal or not. The problem arises from the lack of a acknowledgement. Now that acknowledgement is provided by the second method of asynchronous data transfer, that is the handshaking method, which will be the topic of the next lecture. Thank you. I'll post the schedule on the WhatsApp group and we will discuss queries if you have any.